on Chapter 3, Periodic Table. In 3.2 Periodicity, next you will learn about the ionization energy, which is you have to give the definitions and you have to know the variations across period and down a group. Next, you will see the successive ionization energy. It is used to determine the electronic configurations and the positions of the element in the periodic table. Ionization energy is the minimum energy required to remove an electron from a gaseous atom or ion in its ground state. So this is a general definitions for the ionization energy. And the keywords, must have minimum energy, remove an electron from gaseous atom or ion in its ground state. There are two types of the ionization energy that you will learn. The first ionization energy and the second ionization energy. First ionization energy it refers to the minimum energy must be in kilojoule per mole required to remove an electron from the gaseous atom in its ground state. So for the example, it gives you the magnesium. This is the equations for the ionization energy. Magnesium in gas state must put to the phase of the elements, and when it releases an electron, it will form Mg plus in the gas phase. So for the first ionization energy, it will remove an electron. So this is the energy needed to remove an electron. This is the general equations or general definitions for the first ionization energy. Let's say if the questions ask you to define first ionization energy for the magnesium, so you have to give is the minimum energy in kilojoule per mole required to remove an electron from magnesium atom in its ground state. So magnesium gaseous atom in its ground state. So you have to specify the elements given in the questions. The second ionization energy, it refers to the minimum energy required to remove an electron from positive gaseous ion. Because the stable ion for the magnesium is the Mg2+. So to remove these two electrons, it will remove one by one. And the first one, it removed from the gaseous atom. So this is the gaseous atom and it will form Mg plus gas. And for the second ionization energy, it will remove another electron from the Mg plus gas. Mg plus gas is formed from the first ionization energy. So that's why the definitions for the second ionization energy is the minimum energy required to remove an electron from the positive gaseous ion in its ground state. So if you want to specify the definitions, it is the minimum energy required to remove an electron from the positive magnesium gaseous ion in its ground state. So that is the specific definitions when it gives you the elements. So next, what is the factors that affecting the ionization energy, or short form is the IE. First one is the atomic radius. So if the atomic radius increases or larger or bigger, it will cause the ionization energy decreases. It shows that it needs small amount of the energy to remove the electron if the atomic radius is larger. When the atomic radius is larger, it shows that the attractions between the nucleus and outer electrons are weaker. So it just needs a small amount of the energy to remove the outer electrons. okay, because the attractions already weaker. And effective nuclear charge, ZEF, okay, how it affect the ionization energy is when the effective nuclear charge increases, the attractions between the valence electrons and the nucleus become stronger. So here, when the attractions become stronger, it is difficult to remove the electrons. So it needs more energy to remove the outer electron. That's why as the effective nuclear charge increases, ionization's energy increases. And for the shielding effects, okay, for the shielding effects, when the shielding effect increases, it shows that the attractions between the nucleus and outer electrons become weaker. Okay, so because when the shielding effect increase, the inner electrons, okay, in the inner shell, it will shield the attractions between the nucleus and outer electron. So it will make the attraction becomes weaker. So it's easier for the electron is removed from the atom. So that's why it needs just a small amount of the energy to remove an electron from the neutral atom. So as the shielding effect increases, the ionization's energy decreases. So this is three factors that can affect the ionization's energy. So for the conclusions across period, okay, as the proton number increases, effective nuclear charge increases, so it will cause the attractions between the valence electron or outer electron and nucleus become stronger. So what is the effect to the ionization in energy? It will increases. And down a group, okay, we know that the number of shell principal quantum number increases. So it will cause the shielding effect increases, which is the inner electron in the inner shell. It will shield the attractions between the nucleus and outer electrons. So attractions between the valence electron or outer electrons and nucleus become weaker. So ionization's energy decreases. It just needs a small amount of energy to remove the electron. Let's see the example. Arrange the following in increasing order of ionization energy. So for it gives you the beryllium, magnesium, and calcium. So this is the electronic configurations, okay, for the elements, valence electronic configurations, and group. It shows that all the elements belongs to the same group. So order of the increasing order of the ionization's energy is the calcium is the lowest one, okay, calcium with the lowest ionization energy, magnesium higher compared to the calcium, and the highest one is the beryllium. Okay, why beryllium has the highest IE? This is because because it is in the same group, so we will see the factors of the shielding effects. The first ionization energy decreases on going down a group as the atomic radius increases in order, which is calcium has a larger atomic size compared to the magnesium and beryllium. So it shows that the shielding effect from the beryllium to the calcium increases, and it shows that the attractions between the valence electrons and the nucleus becomes weaker. Alright, so it just needs small amount of the energy to remove the outer electron. That's why the ionization energy is decreased from the beryllium to the calcium. Okay, however, there are also anomalous cases for the first ionization energy across period 2 and 3. From this graph, you can see that from the lithium, okay, to the neon, okay, for the period 2, elements for the period 2, the ionization energy is not increased gradually, okay, because in some parts, okay, they are decreasing of the ionization energy. So you can see between the beryllium and boron and nitrogen and oxygen. Same for the period 3, okay, it happened between magnesium and aluminium and phosphorus and sulfur. Okay, let's see the anomalous cases for the first ionization energy across period 2. The increase of the ionization energy in proton number is not uniform. In the period 2, there are 2 cases, okay, between the group 2 and group 13, beryllium and boron, okay, group 15 and 16, which is for the nitrogen and oxygen. Okay, let's see. What is the anomalous cases for the beryllium and boron for the period 2 is, this is the electronic configurations for the beryllium and boron. So 2p orbital of the boron is well shielded by the inner electron and the 2s electron. Okay, so this is the boron, the electronic configurations. So the outer electron is well shielded by the inner electron in the inner shell from the attractions with the nucleus. So it will cause the attractions become weaker. And what happened? It just need less energy to remove the electron, the outer electron in 2p. So that's why the ionization energy of the beryllium, okay, is higher compared to the boron. Okay, for the nitrogen and oxygen, nitrogen is in group 15 and oxygen group 16. So this is the electronic configurations for the nitrogen and oxygen, and you can see that in orbital 2p of the nitrogen, we know that full orbital p is 6 and half of the orbital p is 3. So for the nitrogen, okay, it is half filled 2p orbital, while for the oxygen, okay, there are 4 electrons in orbital 2p, and we call it as a partially filled 2p orbital. So if we compare the half-filled 2p orbital and partially filled 2p orbital, of course the half-filled 2p orbital of nitrogen is more stable compared to the partially filled orbital. So it will cost more energy needed to remove the electron from the more stable half-filled 2p orbital. So that's why the ionization energy for the nitrogen is higher compared to the oxygen. Okay, next, let's see the anomalous case for the first ionization energy across period 3. So there are also anomalous case in between of the magnesium and aluminium, phosphorus and sulfur. Okay, let's see for the magnesium and aluminium. So this is the electronic configurations. Okay, same as the elements in the period 2. So you can see the aluminium, okay, the outer electron or valence electron is well shielded from the inner electron in the inner shell. So it will cause the attractions between the nucleus and outer electron or valence electron become weaker. That's why it just needs less energy to remove the outer electron. That's why the ionization energy for the magnesium is higher compared to the aluminium. Next, okay, the last one. Okay, so let's see the anomalous cases for the phosphorus and sulfur. Okay, same as the elements in the period 2. For the P, you can see that the 3p3, okay, it is a half-filled 3p orbital, while 3p4 for the sulfur, it is a partially filled 3p orbital. When we comparing the stability of the orbital, of course the half-filled 3p orbital is more stable compared to the 3p orbital. So it needs more energy to remove the electron from the more stable orbital, which is 3p3. So that's why the ionization energy of the phosphorus higher compared to the sulfur. Okay, next, let's see the successive ionization energy. So what is the successive ionization energy? Actually, all the electrons in an atom, okay, have ionization energy. So first ionization energy, we refer to the electron at the outer shell, and the next electron, it refer to the next electron that more near to the nucleus. So successive ionization energy, okay, from the IE1, IE2 and so on of a given element increases because each electron is pulled away from an ion with a progressively higher positive charge. So this is a successive ionization energy. So you can see that the first IE is lower compared to the other IE, okay, because for the example here, okay, you see that there are 5 ionization energy. So the 5th ionization energy is higher. It shows that it is for the electron in the inner shell. So this is the example, okay, ionization energy for the 3 elements, lithium, beryllium and boron. So lithium, we know that it has a 3 electrons. So the first electron ionization energy is lower compared to the second and third. It shows that the third ionization energy is for the inner electron that more near to the nucleus. Okay. So same for the beryllium, okay. The 4th electron, it shows that it is the nearest to the nucleus, and same for the boron. So from the successive ionization energy, you will know how many electrons of the elements have. So for the example, lithium, it has 3 ionization energy. It shows that it has 3 electrons. Same for the beryllium and boron. So let's see the example beryllium atom. Okay, beryllium atom, the first ionization energy is 900 kilojoule per mole. So this is the equations, okay, when it remove an electron from the gaseous atom. So the first electron is removed from the 2s, from the outer electron, and it will form beryllium plus gas with the new electronic configuration 1s2 2s1. And the next ionization energy, second ionization energy, it remove another electron from the gaseous ion, beryllium plus gas, okay. When gaseous atom form beryllium plus gaseous ion, and from this beryllium gaseous ion, it will remove another electron to form beryllium 2 plus gaseous ion. So you see that when it wants to remove the second electron, the ionization energy is higher compared to the first ionization energy because the electron is more near to the nucleus. So this is the second electron removed from the 2s. So same for the next one, okay, the next electron is removed from the 1s. So we know that n equal to 1 is near to the nucleus. That's why the ionization energy is higher compared to the second and first. Okay, and until the last one, when it form beryllium 4 plus, of course that one is the highest one, okay, because it is the only electron, okay, that so it will remove, okay, it will needs more energy to remove the electrons. Okay, so this is a subsequent, okay, the ionization energy of the aluminium. So we have the red dots, it shows the electron, okay. So this is the lowest one, okay, the lowest one, successive ionization energy, it refers to the outer electron or valence electron. So there are 1, 2, and you can see that from the graph, okay, the ionization energy increase, okay, from the outer electron to the inner to the more nearer electron to the nucleus. Okay, so you see that, okay, this is the highest one. Okay, so this is how the first electron is removed, okay, with the lowest IE. It shows that it is located at the outer shell. And second electron, third electron, fourth electron, okay, until 7th electrons. Okay, deduce the electronic configurations of an element and its position in the periodic table based on the successive ionization energy data. So from the successive ionization energy, you can determine the electronic configurations and the positions of the elements. So let's see. By analyze the data of the successive ionization energy, you enable to figure out the positions of the element in the periodic table by looking the highest ratio or sudden increase. So how we see the highest ratio or sudden increase? For the example, we see the lithium. Okay, this is the electronic configurations for the lithium, and this is the first, second, and third ionizations energy. Okay, it has 3 ionizations energy. It shows that it has 3 electrons. So you see that how to see the sudden increase. You can see that suddenly that the electron is removed with a higher energy. So between the second and third, clearly you can see that to remove the second electron, the ratio is quite large. Okay, and you can see that this is a suddenly this amount is increased, okay, compared to the first ionization energy. So it shows that the second ionization energy is the energy used, okay, to remove an electron from the inner shell. So it shows that the electron is the inner electron in the inner shell. So this is an inner electron, and same for this one. So it shows that this is the outer electron or valence electron. So means that lithium has 1 valence electron. Okay, and for the beryllium, okay, you can see that the sudden increase or highest ratio is in between second ionizations energy and third ionizations energy. Okay, from the 1760, it becomes 14,850 to remove the third electron, and it shows that the third electron is the inner electron in the inner shell. So these two, okay, is the outer electron or valence electron, because suddenly, okay, it needs more energy, okay, to remove the third electron. So it shows that this one is the inner electron, energy for the inner electron. So you can deduce, okay, this one as a 2 valence electron. So this is a we call as the highest ratio or sudden increase that occur from the second ionization energy to the third ionization energy. And for the boron, okay, you can see that boron, okay, in between of this one and this one, third ionization energy and fourth ionization energy, sudden increase occur in between third ionization energy and fourth ionization energy. So it shows that the fourth ionization energy is energy to remove inner electron in the inner shell. So it shows that the boron has 1, 2, 3 outer or valence electron. so it is located in group 3. A very large increase in ionization energy indicates the removal of a particular electron involved of an electron from the inner shell, which has a stable noble gas electron configuration. For the example, beryllium. So you see that from this diagram or figure, okay, you can see that to remove the third electrons, okay, it needs more energy compared to the second electron and first electron. So it shows that the first electron is the outer electron, same for the second electron. So the third electron is the inner electron. So this is a okay, same example. So from the lithium, okay, for the lithium, IE2 to IE1, it has the highest ratio or sudden increase is occur from the IE1 to IE2. So these explanations, okay, I have explained before just now. So you can read, okay, your lecture notes. So for beryllium, okay, sudden increase occur in between of the IE2 to IE3 because the third electron, okay, I said that it is a inner electron that removed from the inner shell. Okay, same for the boron. Okay, successive ionization energy. From the data of the successive ionization energy, we can deduce the number of the valence electrons. Thus, okay, you will know the group number of the element, and you also can determine the electronic configurations. For the example, okay, silicon with the proton number 14, and let's say this is a nucleus. Okay, this is a half of the figure for the silicon atom atomic model for the silicon atom. So we have nucleus. Okay, to remove the electrons, okay, we will remove the electron at the outer shell, okay, in the 3p. So that is the first electron is removed. Second electron is removed also from the 3p, and the third electron is removed from the 3s. So you see that the energy, okay, needed to remove the electron is increased, okay, because the electron located in the inner shell, okay, it has more attractions, okay, with the nucleus compared to the outer electron. So okay, same for the other electron. For the inner electron, okay, the energy is higher, increase. Okay, next. So you see that the sudden increase, okay, occur in between of the fourth ionization energy and fifth ionization energy. It shows that energy to remove the fifth electrons, okay, is higher. It is show that highest ratio, okay, with the fourth ionization energy. So it shows that the fifth electron is removed from the inner shell. So it shows that this electron, okay, this energy is for the electron, for the outer electron or valence electron. So it shows that it has 4 valence electrons, and it is shows that the element is located in group 14, okay, and then you can write the electronic configurations, okay, if it gives you the highest end. So this is the explanations, okay, which is there are sudden increase or drastic increase, okay, from the IE4 to IE5, okay. So if you want to use the highest ratio, it will become IE5 to IE4, okay, have the highest ratio. If you want to use drastic increase or sudden increase, it will become sudden increase or drastic increase in ionization energy from IE4 to IE5. So the fifth electron, okay, is removed from the inner shell, which has stable noble gas electron configuration and closer to the nucleus, and it needs much greater energy to remove the electron, and it shows that it has 4 valence electron and it is located in group 14. So the valence electronic configurations or electronic configuration for the valence electron is 3s2 3p2. Okay, and you can complete the previous electronic configuration if the question asks you to give the full electronic configurations. Okay, let's see the example. Okay, it gives you this table, and you can see that the sudden increase is occur in between of the second ionization energy and third ionization energy. So it shows that the third ionization energy is energy for the inner electron in the inner shell. Okay, so the statement is the third electron is removed from the inner shell, which has a stable noble gas electron configuration and closer to the nucleus, and it needs much greater energy to remove the electron, the third electron. So it shows that these two IE for the outer electron or valence electron, so it shows that it has 2 valence electron and it is located in group 2. So the electronic configuration for the valence electron, okay, because the question doesn't mentions, okay, the highest end of the S, so you can give the general electronic configuration for the valence. It is NS2. Okay, let's see another example. So from this table, okay, for the atom M, the sudden increase is occur in between of the IE4 to IE5. So IE5 is the energy, okay, sudden increase is occur between IE4 to IE5. This energy is for the inner electron in the inner shell. So electronic configuration for the valence electron, okay, same as the example 1, because the question doesn't mentions about the highest end of atom N, so you just can give the general electronic configuration for the valence electron. Okay, so there are 1, 2, 3, 4 valence electrons, so NS2 and P2. It is in group 14, and group number of the M in the periodic table is group 14. Okay, why it is not group 4? Actually, successive ionization energy is for main group element. Main group element, we refer to the elements in the block S and P only. Okay, so that's why if there are 3 valence electron, so it is not group 3, it is group 13. Okay, block P. If you said that it is group 3, it is in block D. So successive ionization energy only occur for the block S and block P. Okay, exercise 3. So let's see for this one, for the exercise 3, it needs you deduce the group number, okay, and then the valence electron. So sudden increase, you can see that it occur in between of the 5 and 6 electron. So it shows that this one is the inner electron, energy for the inner electron. So there are 1, 2, 3, 4, 5. Okay, so 5 valence electron. It shows that this element has 5 valence electron and it is in group 15. Okay, 5 plus dengan 10, so it is 15. So the so next, let's see example 3. Deduce the valence electron or group number and valence electronic configuration from the successive ionization energy graph. So here, how you can identify the sudden increase is, okay, when it removes the first electron, this one, second electron, you can see that it is gradually increased. But suddenly here, okay, you can see that it quite quite high, the ratio. Okay, so it shows that here is the sudden increase. Okay, it occur in between of the third electron and fourth electron. So it shows that this one, okay, is the valence electron or outer electron. It shows that this element has 3 valence electron and it is located in group 13. Okay, and the electronic configurations, okay, alright, so this one, okay, if okay, drastic, so this is energy remove. Okay, so the electronic configuration for the valence electron is NS2 and P1, and it is group 13. Okay, so this one, okay, I told you that the successive ionization energy for an element is only applicable for the main group's element. Which one is the main group elements? We refer to block S and block P. Okay, that's all. Thank you.